So in the previous session, we actually saw the general algorithm for this. Now we're going to see some examples of it so that I make sure you all understand all the details of how these things work. Okay, so let's start with a very simple formula, one of the formulas that we saw in the previous session. So let's say my formula phi is next not p. Okay, so this means that my set of atomic propositions, big P, has only one atomic proposition in it, small p. And my formula is saying that in the next step, P will not hold, right? So basically the automaton that I create should accept all the strings in which in the second place, or if you count the indices from 0 in index 1, P does not hold, right? So it's easy to come up with such an automaton on your own, but what we're going to do now is to do it very systematically, just like we talked in the previous session. So, okay. So the first thing that we do is that we compute all of the sub-formulas of this formula phi, and also its closure. So what are the sub-formulas of phi? Okay. We have P here, we have not P, and of course we have next not P. Okay, so this is trivial. You're just computing the subformulas. Now, we said that the closure of phi is the set of all subformulas of phi, but also their negations. So I put P here, but I should also put negation of phi. I already have negation of phi. And then negation of phi is just P, which I already have, so I don't put that again. I have this subformula here, which says next not P. I put it here. And I should also put its negation. So not next, not P. Right? So this is the closure that I have. Okay. Now, what was the general idea? The general idea was that we wanted to have a generalized non-Bookey and non-deterministic Bookey automaton, and we wanted to have a subset of these formulas assigned to each one of the states in our automaton, right? And the idea was that if we start the automaton at that state, it accepts an infinite sequence of letters, if and only if those letters satisfy the conditions that are mentioned by the formulas in that state. Okay? And then we talked about this notion of elementary sets. So what are elementary sets? Elementary sets are all subsets of this closure such that they are, first of all, not contradictory. And secondly, they give us enough information about every one of the subformulas. So for each one of the subformulas, we have to either have the subformula itself or its negation in our elementary set. Okay, so let's go ahead and actually create our elementary sets. And the way we do this is I can have a table, and well, I have to decide whether or not I want P in my elementary set. Then I don't have to really talk about not P, because not P is in my elementary set if and only if P is not, right? And similarly, I need to know whether next not P is in my elementary set or not, but I don't need to have any decisions about this one. So, okay, let's create our first elementary set Q1, and let's say that in Q1 we have neither P nor next not P. Okay, what does this mean? This means that Q1 is basically what? So it doesn't have P, so it must have the negation of P. It doesn't have next not P, so it must have its negation, which is negation of next not P. So this is my set Q1. Okay, now let's talk about set Q2. let's say that this time we have 0, 1. So in Q2, well, I don't have P, so I have to have its negation, but I already have this one. So next not P, so I don't have its negation. So this is my set Q2. Okay, let's continue with this Q3. Let's say this is 1, 0. So Q3 would be P, right? Because I have P here, but I don't have next not P, so I should have its negation. And finally, I don't know why this came like this. Anyway, Q4, let's say 1 and 1. So in Q4, I have both P and next not P. Okay. So actually, for the people in Zoom. Okay. So these are our elementary sets. So what's nice about this? Well, these are basically the subsets of our closure, such that there is no contradiction in them. And also for each one of the subformulas, I know whether that subformula holds or not. So I either have P or not P. I either have next not P or its negation. This is basically what we mean when we talk about elementary sets. Okay. So now, what do we do after this? We said that we create an automaton, and the states in our automaton are basically our elementary sets. So I have an automaton, and the states are, let's say, Q1, Q2, Q3, Q4. Okay, and let me also write the formulas in there. So Q1 was negation of P and not next P. Okay, Q2 is this one. Next not P, and Q3 is P and not next not P. Q4 is P and next not P. Okay. Now, what is the idea? Again, the idea is that if I start my automaton at, let's say, Q3, I want it to accept all the strings that satisfy both of these formulas. Any input that satisfies both P and not next not P should be accepted if I start my automaton at Q3. Okay. Now, so these are the states of the automaton, but then we also talked about how we can actually create the transitions of this automaton. And note that I'm using a very simple formula here. I don't have until in my formula, so we will see an example with until as well. So again, our set of atomic propositions has only one atomic proposition in there, small p, right? So what is my alphabet? My alphabet is all subsets of this. So my alphabet is either P or the empty sets. Each one of these is a letter, right? So whenever I have a transition, I have a transition either by reading the letter P or by reading the letter empty set. Okay. So let's say that I'm at state Q1 and I read the letter P. What should happen? So at Q1, I have this formula that says not P. So if I start my automaton here, I should reject anything that starts with P, any infinite strings that starts with P. So one way of rejecting is to have no transitions at all. So we can say that from Q1, we have no transitions labeled P. So if we are at Q1 and we read P, then we reject. Okay. Now, what if we are at Q1 and we read the empty sets, right? Okay, because we are reading the empty set, we are satisfying not P. Right, so this one is definitely satisfied. But then the other thing is that we should also satisfy this one, not next, not P. What does not next, not P mean? So what should I have in my next step? I should not have not P in my next step. So I should have P in my next step. Right? So wherever I go from Q1, I have to make sure that in my next step, I have P. So from Q1, I can only go to either Q3 or Q4. I can't go to Q2. Right? Because in the next step, wherever that next step is, I should have P. Based on this formula, this is basically saying next P. So in every successor of Q1, I should have the formula P. So from Q1, I can only go to Q3 and Q4. And we already talked about the fact that I can't move with P, so I can only move with the letter that is the empty set. So I can go from Q1 to Q3 with the empty set. And I can also go from Q1 to Q4 with the empty set. And these are the only transitions in my automaton from Q1. Okay, now let's continue this and let's do this for Q2 as well. So in Q2, again, I have not P. So if the input that I'm reading, if the infinite string of letters that I'm reading as input starts with P, then I should just reject. So I just don't put any outgoing edges labeled P. But also in the next state, I should have not P. So where do I have not P? I have not P in Q1, and I have not P in Q2, right? So the successors of Q2 can only be Q1 and Q2, and we can only move with the empty sets as our letters. So these are the transitions out of Q2. Okay. Now let's talk about what happens with Q3. So here now, for the first time, we have P actually. So if in the string that I'm reading as input, assuming that I'm starting at state Q3, the first letter doesn't have P. If the first letter is the empty set, it should reject. Right? It's the exact opposite of the previous cases. And if the first letter has P, then we can actually go to a successor. Now, which successors can we go to? Again, we have this. We have not next, not P. Right? So it means that in the next state, we should have P. So the next state can either be Q3 itself or Q4. So I can go with P to Q4, or I can go with P back to Q3. Okay. Now, what happens with Q4? This is the last state that we have to do in this example. Again, because we should satisfy P, if the first letter that we read is the empty set, we shouldn't have any transitions. So we only have transitions labeled P. Okay. And in the next step, we should have not P. So the next step can be either Q1 or Q2. Right? So I can go to either Q2 or Q1. And these are on labeled P. Okay, so let me actually open the chat here because there are some messages. Yes, this session is also being recorded. Okay, so are there any questions until this part, or is everything clear? Okay, so now, what do we have here? We have an automaton, but we still don't have the accepting conditions, and we also do not have the starting state. So we don't know which states are initial states. But if I start at Q4, for example, what I know is that I will only accept strings that satisfy P and next not P. Why? Because if I have a string that does not satisfy P, then from the very first letter, it gets rejected because there are no outgoing edges, right? So, but if it satisfies P, then the only successors that I have satisfy not P, right? Because I only have edges to Q2 and Q1. So in the next step, if it doesn't satisfy not P, then again, in the next step, it will not have an outgoing edge and gets rejected, right? So actually, I don't really need an acceptance condition here. All I can say is that my acceptance condition is a single set T1, which is all of my states. So Q1, Q2, Q3, and Q4. Why? Because if I'm going to reject, I'm going to get stuck at some point. So as long as I have an infinite path here, it's an accepting path. And how do I say that I accept any infinite path? I say that, well, if you see any state infinitely many times, that's the same as saying if the path is infinite. Okay, so we now know the accepting conditions. But with this accepting condition, and this is, of course, a Boole accepting condition, with this Boole accepting condition, we know that if we start the automaton at Q3, it will accept all the strings that satisfy P and also satisfy not next, not P. If we start the automaton at Q2, it accepts all the strings that satisfy not P and also next, not P, and so on. But what was our goal? Our goal was for our automaton to accept this all the strings that satisfy phi, right? And what was phi? Phi was next, not P, right? So when I want to choose my starting, my initial states in my automaton, I just choose the initial states that include this formula, next, not P. So I don't have it here, I have it here. So Q2 is an initial state. I don't have it here, I have it here. So Q4 is also an initial state. Okay? And this is basically how we translate from this formula to a non-deterministic Boole automaton. Okay? Is this completely clear to everyone? If you have any questions, please ask, because this is definitely going to be in your final exam. Okay, clear? Great. So this was basically an example where, okay, how to get T1 again. Okay, so the question is, how did we get this T1? Well, here the formula that we have doesn't have any until in it, right? So what we said was that let's look at each one of our vertices. Let's, for example, look at Q4. At Q4, we want to accept all the strings that satisfy P and also satisfy next, not P, right? So they should start with P, but then in the next letter, they shouldn't have P. Now, if they start with anything other than P, so if they start with the empty set, then there is no outgoing edge. So we just get stuck here and can't go anywhere else, right? But if they already start with P, we saw that every successor has not P. And this was because, well, in Q4, we wanted to have next not P. So we put edges only to successors that had not P, right? So if it doesn't satisfy next not P, then in the first step, it will either go to Q2 or Q1, right? But then it doesn't satisfy next not P. So in the next step, it gets stuck because it doesn't satisfy not P when it's in Q1, or it doesn't satisfy not P when it's in Q2. So basically, whenever something should be rejected, the way that it gets rejected is that we get stuck and we can't have an infinite path. So we want to accept all infinite paths now. And because we want to accept all infinite paths, that just means that our bookie set is all of the states that we have. Because a path is infinite as long as it visits some state infinitely many times. Okay. So this is the example that we had until this point, the simplest example. And as you saw, this simple example did not have until. And that's why it was so simple. Now let's actually see an example that has until in it. What example can I use? So let's say that my formula phi, let's choose the simplest possible example. Let's say that it's A until B. Okay, and basically the set of my propositional variables is just A and B. So my alphabet, which is all subsets of my propositional variables, is what? It's the empty set A, B, and NP. Okay. Now, again, we start with finding the subformulas. So what are the subformulas of phi? The subformulas of phi are simply just A, B, and phi itself, which is A until B. Right? And then what is the closure of phi? The closure of phi is just its subformulas and also their negations. So A and negation of A, B and negation of B, A until B and negation of A until B. Okay, these are my formulas. Now, the state space is going to kind of get much larger. So we want to compute our elementary sets. And the elementary sets are all subsets of these formulas, such that we either have, first of all, we don't have any contradictions, and secondly, we either have each formula or its negation either. Okay, so I create this table again. So I have to decide what I do with A, I have to decide what I do with B, and also with A until B. Okay. So let's go through this again one by one. Let's start with our elementary set 1, Q1. And let's say that it doesn't have A in there and it doesn't have B. So I don't have A and I don't have B. What does this mean? This means that if I start my automaton at Q1, it only accepts strings in which A and B are both false, at least at the first letter. But can these strings satisfy A until B? Well, of course not, because you have a string, and in the first letter of the string, you don't have A and you don't have B. So this string cannot actually satisfy A until B, right? Because in order to satisfy A until B, there should be some index where you have B, and in every index until then, you should have A. And in your very first index, you're already failing. There is no A and no B. So I have no choice but to put 0 here as well, because A was 0 and B was 0. Okay? So my set Q1 is what? It's not A, not B, and not A until B. Okay. Now let's do Q2. Let's say this is 0 and this is 1. So I'm accepting all the strings that do not have A in their first letter, but have B. What happens with A until B in these strings? A until B would be satisfied. Well, because well, the index that we are looking for, the first index where we have B is just index 0 at the beginning of the string. So here again, I have no choice but to put 1 because I have A and B. I must have A until B. Okay. So Q2 would be not A, B, A until B. Okay. Let's go for the next one. So let's say I have A, but I don't have B. Okay. What should I put here? Can I put 0 here? So is there a, when I say can I put 0 here, what I mean is that is there a string that satisfies A, does not satisfy B, and does not satisfy A until B? Yes. So for example, if you have a string that is just a lot of A's, right, and never has B, so I can put 0 here. Can I put 1 here? Is there a string that satisfies A, does not satisfy B, but satisfies A until B? Yes. So for example, the string that has A in its first letter and B in its second letter, right? So that's going to be another state, 1, 0, 1. So Q3 is A, not B, and not A until B. Okay, instead of A until B, I will just write phi from now on because that's easier. And Q4 is A, not B, and phi, which is A until B. Okay. We have to still continue with this. So what happens if I put 1, 1? So Q5. So I have a, can I have a string that satisfies A, B, and also A until B? Yes. Can I have a string that satisfies A, satisfies B, but does not satisfy A until B? No, because, well, in the very first letter, I have B. So A until B is always satisfied. So here I don't have a choice and I have to put 1. So my state Q5 is just A, B, and phi, which is A until B. Okay, so these are our states now. And you saw the rules that we use for until, basically, right? And this was something that I presented in the previous session. So in the previous session, the rule that we set for until was that if we have 1 here and we don't have 1 here, then we should have a 1 here. And similarly, if we have a 1 here, then we should have a 1 here. Okay. So these are all of our states. Now let's make the automaton. Okay. So my automaton now has 5 states. I have Q1, which is not A, not B, and not A until B. I have Q2, which is not A, B, and A until B. There is Q3, Q4, Q5. Okay, so Q3 is A, not B, not A until B. Q4 is A, not B, and A until B. And Q5 is just A, B, A until B. Okay. So now we have to figure out when we can have transitions. So let's start at Q1. if I want to transition out of Q1, I should be sure that I don't have A and I don't have B. Otherwise, I don't satisfy the requirements of Q1, just like before. So the only transitions that I can have outside of Q1 should be labeled by the empty sets. They cannot be labeled by anything else in my alphabet. So my alphabet is this, and all of them have either A or B. Empty set is the only one that has neither. So all of the edges that go out of Q1 should be labeled by the empty sets. Okay, but where can we go from Q1? So in Q1, we also have this. We have not A until B. Right? Okay, so what happens if I go, for example, from Q1 to Q2? Nothing bad really happens, right? Because basically the fact that I don't have A and I don't have B is enough for me to not have A until B. And then I can basically just go anywhere. Right? So from here, from Q1, I can go anywhere else that I want, as long as the letter that I'm reading is the empty set. Okay. This one was easy. What happens with Q2? So I have not A, I have B, and I have A until B. So the only letter that I can read going out of Q2 is B, right? Because I shouldn't have A and I should have B. Okay? But I also have A until B. But this is already satisfied here because I've again seen B. So I can again go everywhere I want. Oh, and from Q1, I could also go. So from Q2, I write it like this to say that I can go anywhere because I don't want to write all of those edges. So I can go with the letter B to anywhere that I want. Okay. These were not really the interesting cases. We are now getting to the more interesting cases down here. So in Q3, I have A and I don't have B. So the only edges that I can have going out of Q3 are edges that are labeled A. Right? Okay. But I don't want to have A until B. Right? So I have A at this point, but wherever I go, I want to make sure that I will not satisfy A until B. So, for example, I can't go from Q3 to Q2. Well, I can go to Q2, that's fine. I'm sorry. I can't go from Q3 to Q5. Why can't I go from Q3 to Q5? Because if I go from Q3 to Q5, of course, I'm going with the letter A, and then I will satisfy A until B from that point. So I'm satisfying A until B starting from Q3, and that's not what I wanted. I don't want to satisfy A until B. So there is no edge from Q3 to Q5. But is there an edge from Q3 to Q1? Yes, because if I go to Q1, I'm sure that I will not satisfy A until B. So there is an edge that goes here and is labeled A. Is there an edge from Q3 to Q2? No, because if I go from Q3 to Q2, I will satisfy A until B starting from Q2, which means that I would have satisfied it starting from Q3. So there is no such edge. Is there an edge from Q3 to itself? Yes. Why? Because, well, if I take this edge, I will be back at Q3 and I will not satisfy A until B. Is there an edge from Q3 to Q4? No, because it satisfies A until B. Is there an edge from Q3 to Q5? No, because it satisfies A until B. So these are all of the edges going out of Q3. Okay, please stop me whenever you have questions, otherwise I will just continue. Okay, now what happens with Q4? In Q4, I have A and I have not B, right? But I also have A until B. So I'm accepting all the strings that start with an A that do not have B in their very first letter. But I also want to satisfy A until B. Okay. So we had this rule before that we basically said that A until B is equivalent to what? It's equivalent to B or A and next A until B, right? So if you want to satisfy A until B, you should either satisfy B right now, or you should satisfy A right now, and then in the next step, you should satisfy A until B. Okay? Now, what is the case in Q4? The case is that we are not satisfying B, so we are in this case, we are here. So we should satisfy A, which we are satisfying, but also in all of our successors, we should have A until B. So the successors can only be the ones that have A until B. So that's Q4, Q2, and Q5. Right? Now, with which letters can we go to those successors? With letter A, right? Because we shouldn't have B and we should have A. So I can go from here to here with letter A. I can go from here to here with letter A. And I can just do this with letter A. Okay. Now, finally, what happens at Q5? At Q5, we have A and B and A until B, right? So first of all, any edge that goes out of Q5 should be labeled by AB. Oh, and these labels should be sets, right? Sorry about that. I forgot to put the sets notation. These are all sets. Okay. So any edge that goes out of Q5 should start with the letter AB. And it should also satisfy A until B. But it satisfies this trivially. Why? Because we already have B in the very first index. So as long as the letter that we read is AB, it doesn't matter where we go from Q5. So again, I have an edge to everywhere. I don't care where. And it's labeled AB. Okay. So this is the construction of the automaton. Now, just like before, we have to talk about our accepting condition. Okay. But now for the first time, we actually have until in our formula, and this is where things get much more complicated. See, the way that we were handling until was using this formula here, which is basically called the expansion formula. And especially we applied this in Q4, right? So what's happening in our, let's just see what's happening in our intuition when we are at Q4. When we are at Q4, we want to accept all strings that satisfy A, not B, and also A until B, right? First of all, if we have a string that doesn't satisfy A or that doesn't satisfy not B, then we don't have any outgoing edges, just like the previous case, and we get stuck. So the first good rule of thumb is to say, okay, I only accept paths that are infinite. So I define my first Boole target set, T1, as the set of all states, Q1, Q2 to Q5. So what this says is basically like the previous case, that I only accept infinite paths. I reject all the finite paths. Okay, but we still have more to do. So if I'm at Q4 and I don't satisfy A or I don't satisfy not B, then I will have a finite path and I get rejected. But what's there to make sure that I satisfy A until B? So the idea was that in order to satisfy A until B, you should either satisfy B right now, or you should satisfy A right now and then promise that you will satisfy A until B in the next step. Okay? So here I'm using that promise. I'm saying that I satisfy A right now, I don't satisfy B, so this part is not there, but I promise that in the next part, in the next step, I will satisfy A until B. Now, what is the problem? The problem is that there are paths here that do not actually honor that promise. So for example, there is this cycle here. I can go infinitely many times through this, and I will never get to a state that has B, right? Can you find any other cycle like that? Well, not in this graph, right? Because if I go here, I already have B, and if I go here, I already have B as well. So the problematic thing is that I can just go here infinitely many times. And this basically means that at every point in time, I'm saying that, okay, I don't have B right now, but I have A, and I promise that I will have B sometime in the future. But every time in the future, I'm just making the same promise without actually honoring it, without actually visiting a B, because I'm just going around here. So we want to avoid this. How can we avoid this? Well, we can basically just say that don't stay in Q4 infinitely often, right? We can, for example, say that you should be in Q4 only finitely many times. That would make our life easy, but that's actually kind of a big deal. It's more than we need. What we need is to say whenever you are at Q4, later on you should visit a state that has a B in it. So basically, whenever you make this promise that I will see B sometime in the future, you should be sure that you honor this promise. Okay. And this was actually the last rule that we saw in the previous lecture. So if you look at the lecture notes of the previous lecture, there is this last part where it says that we basically define a new target set. And let's call this the target set of A until B. And what was the definition? The definition was that this is all the states Qi such that either B is in Qi or the until A until B is not in Qi. Okay. So I use this as my second cookie objective. So I'm creating a generalized cookie automaton. So a word is accepted if and only if it visits T1 infinitely many times, and it also visits this one, T of A until B infinitely many times. But let's see which states are these. So I want all the states that either have B or do not have A until B. So those that have B are Q2 and Q5, right? Those that do not have A until B are Q1 and Q3. So everything other than Q4. So what I have here is Q1, Q2, Q3, Q5. Okay. What does this tell me? This tells me that a run is accepting if and only if it visits this set infinitely many times, right? So what runs are being excluded? The runs that just cycle through Q4 forever, right? As long as you don't cycle through Q4 forever, you will visit the other ones infinitely many times. So this is exactly the same as saying you have to keep your promise. And when you promise that you want to see B, you have to actually see B. You have to actually go out of Q4. Okay. Finally, what are our starting states? So what are our initial states Q0? Q0, we said, is the set of all states that have our target formula phi in them. And phi was A until B. So here, I don't have A until B here. I have A until B in Q2. So Q2 is an initial state. I don't have it here. I have it in Q4. So Q4 is an initial state. And I have it in Q5. So Q5 is also an initial state. So our initial states are Q2, Q4, and Q5. Okay. Does this make sense? Any questions or doubts? Do you all agree that this automaton accepts A until B? Okay, great. So finally, hopefully if we can do this in time, we can do the example that I was doing in the previous lecture. And this is an example that has both until and next. So let's say that my formula phi is now A and next A until A and not next A. Okay. So now I have both until and next. And the set of my atomic propositions is just A. So my alphabet is the subsets of this, which is A and the empty set. Okay. So again, subformulas and closures. Subformulas. What subformulas do we have? We have A, we have next A, we have A and next A, we have not next A, we have A and not next A, and we have the whole formula phi. These are our subformulas. Right? And just to save space, I'm going to call this one psi1, and I'm going to call this one psi2. Okay. So my subformulas again are now A, next A, psi1, not next A, psi2, and phi itself. Okay. So what is my closure? My closure is just my subformulas and their negations. So A and also not A. Next A and also not next A, which was already there. And then we're going to have psi1, not psi1, psi2, not psi2, phi, and not phi. Okay, this is our closure. Now, how many items do we have? How many formulas do we have in our closure? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 different formulas in our closure. And well, we saw that our elementary sets are subsets of our closure, right? So this would mean that we can potentially have up to 1024 elementary sets. But that's not going to happen. Why? Because we said that our elementary sets should actually not be contradictory, and they should also give us complete information about every formula, whether that formula holds or its negation. So let's do our elementary set computation. Okay, so what should I put here? I should put A, I should put next A, I should put psi1, which is A and next A. I should put psi2, which is A and not next A. And I should have phi itself, which is psi1 until psi2. So psi1 until psi2. Okay. So let's do this. So let's say that I don't have A and I don't have next A. Now, because psi1 is A and not and next A, and I don't have either one of them, so I can't have psi1. Psi2, again, I can't have psi2 because I don't have A. Now, what happens with phi? Phi is psi1 until psi2. I have neither psi1 nor psi2, so I cannot have phi either. Okay, next one, Q1. So let's say that I start with 0, 1 this time. So I don't have A, I can't have A and something. I don't have A, I can't have this. I don't have psi1, I don't have psi2, so I can't have psi1 until psi2. Look at Q2. So in Q2, let's say that I have A and I don't have next A. So I have A, but I don't have next A, so I can't have A and next A. I have A, I don't have next A, so I have not next A. So logically, I should have A and not next A. So this is fine. Now, I don't have psi1, but I have psi2. And so because I have psi2, I definitely also have psi1 until psi2. Because psi2 holds right now, so psi1 until psi2 also holds. Okay, next state. So let's say that now I start with 1, 1. So if I start with 1, 1, I have A and I have next A, so I should have A and next A. Here I don't have not next A, so I can't have this. What happens here? So I have psi1 at the moment, but I don't have psi2. So it's possible that I have psi1 until psi2, and it's also possible that I don't have it. Right? Why? Because, well, you can, in the first, at the first index of the string, psi1 holds, but psi2 doesn't hold. So it might be the case that psi1 keeps holding until at some point we see psi2, and it might also be the case that we just never see psi2, or any other condition that psi1 until psi2 does not hold. So I can have this with a 1, and I can also have it with a 0. Okay, and again, now I'm not going to write these sets anymore, but you basically know how to read them, right? So Q2 has A, not next A, not psi1, psi2, and phi. This is how we read each one of these. Okay. So these are the sets of states that we had. So before going into the construction of the automaton itself, which are our initial states here? Our initial states are all the states that have our formula phi in them. And this is Q2 and Q3. So these are the initial states. Okay. Now, I'm not going to construct the whole thing because that's going to take a long time. But let me just do some of the transitions. So let's say, first of all, that I'm at state Q3. Okay. So let me put this here. You can see it. So again, this was A, this was next A, this was psi1, this was psi2, and this was phi. Okay, so if I'm in Q3, okay. So if I'm in Q3, what do I know? I know that I should satisfy A. So the only letter that I can read to go out of Q3 is A. So I cannot have anything going out of Q3 with any label other than A. Okay, so from Q3, I can only go out with the label A. But where can I go to? Look at this list and tell me where can I go to from Q3 reading A. Okay, if I'm at Q3, I should satisfy A, but I should also satisfy next A. So I cannot have any successor that does not satisfy A, because all of my successors should satisfy it, right? So I can't go to Q0, I can't go to Q1. Right? Can I go from Q3 to Q4? Why not? So at Q3, I'm satisfying phi, which was psi1 until psi2. And I'm not satisfying psi2. So this is one of those cases where I'm just promising that, okay, for now I satisfy psi1, and then later on I will satisfy psi2. So wherever I go from Q3, I should keep that promise and have phi as well. And I don't have phi in Q4. So from Q3, I can only go to Q2 and Q3. So I can go to Q2 with the letter A, or I can go back to Q3 with the letter A. Okay. So this is the case of Q3. Now let's do Q2. What happens in Q2? In Q2, first of all, I can, again, because I should satisfy A, I can only have outgoing edges that are labeled with A from Q2. Okay, so that's for the labels, but I should not satisfy next A. So I can only go to successors that do not have A. So I can only go to Q0 and Q1, right? Okay, but can I go from Q2 to Q0? Can I go from Q2 to Q1? Well, we have to again check this with our until conditions. So at Q2, I should satisfy psi1 until psi2, which is phi. But I'm already satisfying psi2. So it's satisfied, and I don't have any other conditions on my successors from this until. So from Q2, I can go to Q0 or Q1. So from Q2, I can go to Q0. Let's label A again. Or I can go to Q1 with label A. Okay, and we just continue like this and do this for all of our states. And the automaton that we get in the end is this one. So let me just draw the whole automaton. This was also in the lecture notes of the previous lecture. So we have Q2, Q3, Q0, Q1, Q4. And these are the starting states. From Q3, I can go to Q2 with A, or I can go back to itself with A. From Q2, I can go to Q0 with A, or I can go to Q1 with A. Okay, from Q0, I have these edges. From Q1, I have these edges. And from Q4, I can only go to itself. Okay. So this is our whole automaton if we go through all of these steps. Now, okay. So we talked about which states are our initial states, and these were the states that have phi in them, so Q2 and Q3. But now let's talk about our accepting state, our accepting condition. So first of all, we said that we should have this Boole set T1, which is all of our states, Q0, Q1 to Q4, because we want to reject any path that is finite. But then we also have an until, right? So we have our main formula phi, which is psi1 until psi2. So we should have also a set for that, psi1 until psi2. And what is this set? This is the set of all states such that what? What was the condition? So it's that either psi2 is in the state or the until formula, which is in this case phi, is not in the state. Right? So basically, if we visit this set infinitely many times, it means that whenever we visited a set that had phi, we had to later on visit a set that had psi2. Right? So whenever we made a promise to see psi2 in the future, we kept that promise. This is the intuition behind this set. Okay, but what is this set exactly? So you should either have psi2 or not have phi. So you don't have phi here, here, and here, and you have psi2 here. So it's everything other than Q3. So it's Q0, Q1, Q2, and Q4. So again, what's the bad case that we are avoiding? The bad case that we are avoiding is that we are in Q3. So in Q3, we are promising that we will see psi2 in the future, because in Q3 we have phi. In Q3 we have phi. So we are promising that we're going to see psi2 in the future. Okay, what is psi2? Psi2 is A and not next A. So what we are promising is that sometime in the future, we're going to get to a letter where we have A right now, and then in the next step, we don't have. Right? Now, what this target set is saying is that you cannot go to Q3 and just get stuck there. Why? Because if you just get stuck here and go in this cycle over and over again, you're just seeing A. So you are breaking your promise that at some point you get to an A that is followed by not A, right? So basically this tells us that our Boole set should be all the states other than Q3. And then this whole thing is a generalized non-deterministic Boole automaton. So a run is accepted if it visits both of these sets, both T1 and T of psi1 until psi2, infinitely many times. Now, in this case, this one is a subset of that one. So the only thing that we care about is this one. This one should be visited infinitely many times. Okay, any questions? Okay, great. So based on this, I can now go back to the slides of the previous session, and hopefully they make much more sense now. Okay. So. Let me change this thing here as well. So we had a bunch of rules in the previous session. There were a bunch of rules for how we create the elementary sets, right? And these were the rules that you saw in these examples today. So these were the rules. We had the basic propositional logic rules that said that if you have a formula psi, then you shouldn't have not psi in the same set, and vice versa, right? And also, if you have psi1 and psi2, then you should put their and in there as well. And another thing, well, this one didn't really happen in our examples, is that if you have true in your formulas, then true should appear everywhere in every one of your elementary sets, because true is always true. Okay, so true always holds. Now, the next set of rules that we had to follow when creating our elementary sets were these. They were basically about until and also about next, right? No, okay, just about until. Yeah, because next will be handled by our transitions. So basically there was this idea that if you have psi1 until psi2 in your elementary set and you don't have psi2, then you'd better have psi1, right? Because if you don't have either one of these, if you don't have psi1 and you don't have psi2, you're definitely not satisfying psi1 until psi2. And we saw an example of this. And another thing is that if you have psi2, then it doesn't matter if you have psi1 or not. In any way, you have psi1 until psi2 as well. Because if psi2 holds at the current moment in time, then psi1 until psi2 holds at the current moment in time. Okay, so these were the rules that we saw for creating the elementary sets. Now, then the rules that we have for creating the transitions are these ones basically. So the first rule was the rule that I was using over and over again when I was saying that we only have transitions that are labeled blah, blah, right? So whenever you want to go out of the current state, so if your current state is, let's say, Q, and the letter that you have read is WI, then WI should satisfy all of the atomic propositions that you have in Q. So if at the state I knew that I should satisfy B right now, then the letter that I read should have B in it. Otherwise, I can't move anywhere, and I'll get a finite pass and I get rejected. Okay, so this was this rule. Now, this is the rule for next. The rule for next says that if right now you are computing the transitions out of a state Q, and in your current state, you have the formula next psi. What does this mean? This means that no matter where you go, in the next state, when you get there, you should satisfy psi. So if you go from Q to Q prime, and you have next psi in Q, then you should have psi in Q prime. This was the rule for next. Now, we also had this rule for until, that, well, if at the current point, if in Q, I have psi1 until psi2. This was the part where I was talking about making a promise. Then I should either have psi2 right now, which satisfies this, or I should have psi1 right now and promise to have psi1 until psi2 in the next step. So this is also the rule that we have. So either psi2 is holding right now at Q, or psi1 is holding right now at Q, and then the psi1 until psi2 formula holds in the next step at Q prime. Okay, these were the rules that we had. And this is actually the last example that I did right now. And then finally, we had this accepting condition, right? And the accepting condition was that if you have a formula that has until in it in this format, psi1 until psi2, then whenever you get to a state that has psi1 until psi2, you have two choices. You either satisfy psi2 right now, or you go to another state that satisfies psi1 until psi2. But the problem was that you could get into a cycle. Well, in our examples, the cycle was just a self loop, right? But you can get into any type of cycle, and you can basically just at this point say, okay, I satisfy psi1 right now, and I promise that I will satisfy psi2 in the future. Then here, again, you do the same thing. You say, I satisfy psi1 right now. I promise that I will satisfy this in the future. But you never keep the promise, and you just keep promising. Right? So you never see psi2. And this was a bad case. So in order to avoid this bad case, we defined this other Bookey set, which is the set of all states that either have this second part of the until or do not have the until itself. So what this forces us to do is to, whenever we get to a state where we have until, we can't just promise forever and get into a cycle. We have to, at some point, get to a state that actually has psi2 in it. Okay. Yeah, so that's pretty much it. I just wanted to say one small word about the runtime again. So if you start with a formula phi, and let's say that the length of your formula is n. So let's say that the length of this formula is n. So how many subformulas can you have? Every subformula is also a substring of this formula. So you cannot have more than order n squared subformulas, right? So the closure of phi has at most order n squared formulas in it. And our elementary sets were subsets of the closure. So we have exponentially many elementary sets in the worst case. So in the worst case, the size of our automaton is exponential in the length of our formula. And this is probably the most important thing to know here. So whenever you have an LTL formula, you can translate it basically to an equivalent non-deterministic Bookey automaton or general non-deterministic Bookey automaton. And the size of the automaton is exponential in the size of the formula. Okay, so that's all for this session. Please feel free to ask any questions that you might have. And let me stop the recording before that.